According to the U.S. Environmental Protection Agency, Americans spend a whopping 90% of their time indoors. Now, indoors, concentrations of pollutants may be significantly higher than in outdoor levels. Consequently, indoor environmental quality is a major concern of buildings. Strategies to improve indoor environmental quality have the potential to enhance the lives of building occupants, increase the resale value of the building, and even reduce liability for building owners. Personnel costs, which are primary salaries and benefits, are much larger in a typical building operating cost budget compared to electricity and maintenance. So, strategies that improve employee health and productivity over the long term can have a large return on investment. In addition, preventing problems is generally much less expensive than dealing with any illness or loss of productivity that can stem from poor indoor environmental quality. Building owners, designers, and operators should aim to provide stimulating and comfortable environments for the occupants, as well as minimize the risk of building-related health problems. Meeting this goal requires attention to two separate issues. First off, we have indoor air quality. Now, this is distinct from indoor environmental quality in that it focuses just on the air itself. And secondly, we have comfort. Now, this includes thermal comfort, it includes lighting, as well as acoustics. Within the last decade, there has been an ever-growing attempt to quantify that cost-benefit that relates to green building as it pertains to improved worker productivity and health. While much more difficult to quantify than the cost of resources, such as energy or water, the potential cost-benefit of healthier, more productive environments appears to be the potential goldmine for return on investment of green buildings that offer improved indoor environmental quality. So what we see here is the results of a Greg Katz study which shows the cost per square foot over a 20-year period. So let's take a look at some of these numbers. Now the energy savings is significant, $5.80 over that 20-year period. Now that corresponds with a $3 to $5 cost premium over the same period. So on energy savings alone, this project is already in the positive when it comes to investments towards green building. However, that is a rather non-compelling investment return in terms of 80 cents at the top level of the costs associated. But then we drill down even further. So we have emission savings, we have water savings, we have operations and maintenance savings. But where the real money starts to come in is the productivity and health value associated with these improved environments. So $36, almost $37 to $55 per square foot over that same 20-year period in terms of return to the building owner. Now that's based on the expenditure of $3 to $5 basic building costs for that same building. The total 20-year net benefit, now here's where we start to really dial in these numbers, is almost $50 to $66 per square foot. So in terms of savings on a square footage basis, there are amazing opportunities here with LEED, and thinking about the productivity and health value is really where those big numbers start to tally. Here we see our prerequisites. So you'll note we have minimum indoor air quality performance. There is a corresponding credit to that prerequisite. We also have environmental tobacco smoke control, and because this one's so fundamental, there really is not a corresponding credit. And then for the LEED for Schools program alone, we have a minimum acoustical performance prerequisite as well. And looking at our credits, we have enhanced indoor air quality strategies, going essentially beyond those prerequisite criteria. Low emitting materials, construction, indoor air quality management, air quality assessments, thermal comfort, interior lighting, daylight, views, and finally acoustics. Now jumping feet first into our first prerequisite credit combination in the category. Minimum indoor air quality performance and then enhanced indoor air quality strategies. The intent here is to contribute to the comfort and well-being of building occupants by establishing minimum standards for indoor air quality. Now there's a couple of pieces to this prerequisite criteria. First of all, we have different spaces that are addressed. So we have mechanically ventilated spaces and then naturally ventilated spaces. We have both ventilation and then control criteria. So regarding the ventilation criteria, of mechanically ventilated spaces. First, we adhere to option 1, which requires compliance to ASHRAE standard 62.1/2010. Now, this specific ASHRAE standard has a couple of different ways of calculating minimum air delivery. What we're specifically looking at here is the ventilation rate procedure criteria using sections 4 to 7 of this standard, and that dictates the amount of outdoor air that needs to be delivered to each individual space based on a host of criteria, including the number of occupants present. Now, option 2 is specific to non-US projects and allows these European and other projects to follow those CEN standards that are perhaps more familiar to those engineers. Now, looking at the monitoring criteria, we have, again, two different ways of thinking about this. We have variable air volume systems, which are where they modulate the quantity of air that's delivered to a space to maintain a standardized temperature profile. Now, with constant volume systems, there's a consistent and rather constant volume of air that's continuously delivered to that space, and rather than modulating the amount of air that's provided, they instead modulate the temperature and perhaps humidity of the air that's actually being delivered to that space. For naturally ventilated spaces, when we're talking about the ventilation criteria of, again, the prerequisite itself, there needs to be a minimum air opening. Now, this is dictated again by ASHRAE 62.1/2010, of course, or local code if that happens to be more stringent, and requires that it follows section 4 to determine the amount of opening area that needs to be provided. So these are openings to the outdoors, measured in terms of square footage. Now, using CIBSE AM10, that allows project teams to consider the ventilation and whether or not it's going to be effective in that space. So in addition to following CIBSE AM10, we also need a minimum opening as dictated by ASHRAE 62.1/2010. So this gets a little bit tricky when considering naturally ventilated spaces, and likely falls to the mechanical or architectural designers in terms of determining that this is going to be an effective strategy. Now, on the monitoring side, it's much like the mechanically ventilated space, although there's some subtle differences. So first of all, we need to measure the exhaust airflow, making sure that it doesn't deviate by more than 15% from what's anticipated, and if it does, then there needs to be an alarm sent to the building operator or the occupants. CO2 monitoring. Now, this is fundamental here at the prerequisite level, needs to be within the breathing zone. So this is not in the return air duct. This is present in the thermally conditioned zone so that it's ensured that the air quality is maintained for occupants within these spaces. There are some additional criteria for residential spaces, and big picture, this aligns with the LEED for Homes program. So no unvented combustion appliances, carbon monoxide monitoring needs to be put into place. The indoor fireplaces need to have either glass enclosures or some sealed doors. Combustion-based space and water heating must be closed combustion and have a power vented exhaust or be located in a detached utility building or an open air facility. And finally, residential projects that have radon potential, and LEED defines that as the 4th floor or lower within a LEED for new construction or LEED for residential project, need to have radon mitigation procedures as well. Now, jumping into the credit criteria, there's several facets to this. So we're looking at mechanically ventilated, naturally ventilated, and then mixed mode, which is essentially a combination of those first two options. Each different space, depending on the ventilation strategy, needs to meet 2, 3, or potentially even all 5 criteria here to comply with these credit criteria. And here we look at the specific criteria as it applies to each individual process within each area. We have the entryway systems, cross-contamination prevention filtration, and then those naturally ventilated areas and mixed mode ventilation areas as it pertains to the design calculations. So for the entryway systems, we need a 10-foot walk-off mat system. Now, this can be a permanently installed grate or potentially a rollout mat system as long as they're maintained consistently. There's a special way of thinking about warehouse areas. In fact, those are basically considered outdoor areas for the purpose of this credit. What that means is that we don't concern ourselves with the entryway systems between outdoors and the warehouse area. We're specifically considering those transition points between the warehouse and the other conditioned floor areas within the building. Now, the last point I'll make around entryway systems is that LEED for Healthcare has some very specific and alternate criteria here. And what that represents, or really tries to address, is the fact that there may be a higher likelihood of pathogens within these types of projects. So pressurized entryway vestibules here are the strategy to keep in mind to contribute to minimizing the potential for contamination. In addition to the entryway systems, we also address interior cross-contamination prevention so that those chemical use areas are prevented from contaminating adjacent spaces. Filtration here is important as well, so any outside air system that delivers that outdoor air, which may or may not have a high level of particulate within the air, needs to be filtered, either using a MERV 13 or Class F7, which is essentially compatible with MERV 13, but reflects the European standard of measuring filtration. For the natural ventilation side of things, we need to use, again, that CIBC Applications Manual 10. We need to make sure those strategies are appropriate given the context of the overall building. And then finally, for those mixed mode applications where we have mechanical ventilation some of the time and natural ventilation the rest of the time, we need to make sure that the project itself complies with the CIBC Applications Manual 13, and that's the 2000 version. And now we consider option 2, which has its own suite of complexity here. Option 2 looks at requiring projects to meet applicable requirements, again, dependent on whether they're mechanically ventilated, naturally ventilated, or the mixed mode application. So we have 5 criteria here, again, dependent on what type of project you're looking at. We have exterior contamination prevention. So here we're looking at minimizing pollutants that can enter the building directly. So this is measured by either CFD, modeling, or computational fluid dynamics, or Gaussian dispersion analysis. So there's a lot of very high-tech ways to think about this, but essentially that requires simulation within a computer to make sure that that exterior contamination is successfully prevented. Part B here looks at increasing ventilation. So this is very simple. 30% beyond the prerequisite. So if the prerequisite using ASHRAE 62.1 2010 said you need to provide 20 cubic feet per minute to this space, all of a sudden you'd need to hit 26 or 30% more, so 26% based on that minimum criteria going 30% beyond. CO2 monitoring is a special case here and needs to be present within the densely occupied areas within what they call the breathing zone. Now that's between 3 and 6 feet above the finished floor. There needs to be either an alert that goes to the building operator that would let them know that, hey, maybe we've got a CO2 problem here, or a visual or auditory alarm that goes to the occupants in the space. For areas where there may be potential contaminants in addition to carbon dioxide, so say you have an area that uses high volume copying equipment. Now there may be sources of potential air contaminants within that space. Using an alarm tuned to recognize specific contaminants within the air whenever unsafe conditions arise is the way to address this credit. And finally, we have the natural ventilation criteria. So again, using that CIBC AM10 requires projects to look at those design calculations within the standard that confirm very clearly whether the project is going to have effective natural ventilation or whether it may fall short. And our strategies. So first, projects should use ASHRAE 62.1 2010, focusing specifically on the ventilation rate procedure. I'm going to say that again, the ventilation rate procedure, not the indoor air quality procedure. Ventilation systems look at the number of occupants and those habits of the occupants within the space to determine the minimum outdoor air ventilation requirements. It's critically important to make sure that the balance of outdoor air delivery and energy efficiency are calibrated to meet the owner's project requirements. Now, this is so important. Delivering additional air to a space sounds like a great idea, right? So we've got so much air that we're delivering to a space. Keep in mind that there's absolutely an energy impact to delivering all of this additional air. So while from a human health and indoor air quality perspective, it's a good thing to continue to deliver ever more outdoor air, we start to approach a point where the returns aren't worth it in terms of energy input relative to improved air quality. So balancing those two concerns is fundamental and reflects a critical concern and standard practice, rather, within sustainable design in weighing those trade-offs. So on one hand, we have better air quality in the building, and on the other, we have increased energy use. So taking those two competing considerations and finding that sweet spot is really the art of sustainable design. The final point to mention here is that inadequate ventilation can potentially cause a lot of problems. So we can have poor air quality. That can cause a lot of problems, looking at illness potentially, liability for asthmatic response or the like. So managing this at the outset during design ensures that the likelihood of those problems arising later throughout the building's life cycle are minimized. Now, this is by far my very favorite example in the whole program. We have here a swine barn, which is exactly what it sounds like. A big building, relatively unconditioned, where they keep pigs. So within this swine barn, which is 8,100 square feet, we have a whopping 3,400 square feet of operable wall area. Now, typically we say operable window, but in this case, we're talking about roll-up barn doors, which absolutely represents operable area where you can increase the amount of open air penetration so that fresh air can come in. This is 43% in terms of a ratio compared to the floor area. Now that blows away the criteria here for a minimum operable wall or window area to meet the credit requirements. Now, keep in mind, this is a place where they keep live pigs. So the fact that they have a humongous operable wall area is not necessarily inappropriate given the context of the program needs of the space. So we're clearly meeting the criteria here in terms of percentage of operable wall area relative floor area. But in addition, it is a swine barn where odors, of course, would be a likely consideration by those designers. And finally, our question. The minimum ventilation rate for mechanically ventilated spaces is determined by what? Okay. Well, our correct answer here is number 3, and the section number is not necessarily something you'll be quizzed on, but the fact that we're focused on the ventilation rate procedure itself is quite important. So keep in mind, we're looking at the ventilation rate procedure within ASHRAE 62.1 2010 and not the indoor air quality procedure. And our next prerequisite, EQ prerequisite environmental tobacco smoke control. Here we're looking to prevent or minimize exposure of building occupants, indoor surfaces, and ventilation air distribution systems to environmental tobacco smoke. Now there's a couple of pieces here to the requirements. First of all projects need to do several things. So they need to prohibit smoking within 25 feet or 7.5 meters of all entries, outdoor air intakes, or operable windows. They also need to prohibit smoking outside the property line, anywhere there's going to be business practices taking place. So think about a sidewalk sale or outdoor sidewalk seating for a restaurant. Now, there may be jurisdictional criteria, and in fact, we talk about that exemption here in a minute. so I don't want to go down that path yet. But fundamentally, you need to prohibit smoking anywhere there's business activities ongoing. And then there needs to be no smoking signage, which states clearly that policy that confirms no smoking within 25 feet of the entryways and no smoking within 25 feet of the air intakes or operable windows within just 10 feet of all building entrances. So with that in mind for all projects, now we look at two different types. So non-residential projects. This is really, really simple. Not trivial to accomplish for certain types of projects, but it's really, really simple. No smoking, period. No smoking in the building, no ifs, ands, or buts. That's simply the requirements. Now for residential projects, there's two ways to approach it. You can, first of all, prohibit smoking. Really simple again. The other approach here is allowing smoking in certain dedicated residential units. Perhaps it's all, perhaps it's one or a small number of them. It can be any number. But regardless of the number of smoking spaces in this residential facility, smoking needs to be prohibited in all common areas, and then there needs to be extensive mitigation strategies put into place to minimize or eliminate the cross-contamination from those areas where smoking is allowed, transitioning to those spaces where smoking is not. So looking at these strategies, first of all, I mentioned this exemption. So the 25 feet criteria is great when you own all the property within 25 feet of any building entrance. Problem is that's not always the case, especially when looking at storefront businesses. Now, LEED recognizes that it may not be possible for the building operator or owner to prohibit smoking within 25 feet of the building entrance if, say, 5 feet from the entrance you're all of a sudden on a public thoroughfare. Now, it's encouraged that the building owner prohibit smoking within those 25 feet, but where that's not possible due to jurisdictional criteria, it's acceptable to verify that to USGBC, or GBCI rather, during the certification process, and confirming that the project has no ability to dictate smoking habits outside of its property line. When that's the case, it's okay to not extend that non-smoking boundary outside of the project's property line itself. LEED for Schools has a little bit more stringent criteria here and essentially requires no smoking on the property, period. And there needs to be signage at every single property entrance so that building visitors know that that is a mandatory criteria for their continued presence on campus. The last point to mention here is that even if a project's smoking area is located 25 feet away from the building, which would obviously also comply with the air intakes and the operable window criteria here. So clearly we're outside of the boundary of where it's unacceptable to designate your smoking area. It's worthwhile for project teams to consider where that smoking area is going to exist in the context of the actual usage patterns of that project. So if there are pedestrians or any sort of pathway passing right through that smoking area, it may be worthwhile to reconsider that location so that non-smokers, or gosh, even smokers who aren't currently lighting a cigarette, would be able to walk through there without additional exposure to that secondhand smoke. So making sure that the environmental tobacco smoke is not affecting the residents and occupants of the building is fundamental here. So whether or not you're meeting the letter of the requirement by keeping it 25 feet away from the building, it's worthwhile to consider making sure that that non-smoking area is also removed from those pedestrian pathways. And now our question. If there is a designated smoking area outside the building, it must be 25 feet away from the building's what? So select 3. And the answer is 1, 3, and 4. Operable windows, entryways, and outdoor air intakes. Indoor environmental quality credit acoustic performance. The intent is to provide workspaces and classrooms that promote occupants' well-being, productivity, and communications through effective acoustic design. Now, within this credit, there are 4 specific criteria. First, we have HVAC background noise and sound transmission. We'll talk about the next 2 here in a minute. But for the HVAC background noise, first of all, you need to meet the most stringent criteria of either the 2011 ASHRAE Handbook, the HVAC Applications, Chapter 48, Table 1, or the AHRI Standard 885, 2008, Table 15. The other criteria that projects may be held to are local equivalencies. Now, meeting those design criteria for HVAC noise levels from sound transmission requires the project team address all of those HVAC ducting systems as well as the units themselves. On a sound transmission basis, this requires that projects use composite wall systems and glazing systems and any separation system between spaces. For sound transmission criteria, project teams need to have wall assemblies and inner wall interior windows that meet minimum STC ratings. Now, these represent the sound transmission coefficient between, or rather through, these wall systems. So it basically reflects the amount of sound that's going to be transmitted from one space to an adjacent space. We also look at reverberation time. Now, there are minimum criteria of reverberation time between different spaces, and all of these are listed in the LEED reference guide, but keep in mind that there are specific criteria around RT for every single type of space within a building. And then finally, we have sound reinforcement or masking systems. So these are essentially speaker systems or white noise systems. And for large conference rooms, the space needs to be addressed and considered whether or not it requires these sound reinforcement systems. And those white noise systems cannot exceed 48 decibels. In terms of strategies, there's also the additional requirements that apply to LEED for schools. So LEED for schools also need to meet prerequisite criteria. So here we're talking about the credit, but schools have that prerequisite as well, addressing background noise, exterior noise, which is not something we talk about here in the credit, the RT, and specific criteria around classrooms and core learning spaces, recognizing that the student-to-teacher and student-to-student communication is really core, is really central and fundamental to the program needs of that space. The last point I'm going to mention here is that LEED for Healthcare has additional criteria around sound transmission. And the reason for this is because of the very sensitive nature of patient-doctor conversations. Now, it's important to know that there are a lot of very special confidentiality requirements when it comes to those types of conversations and all of the very sensitive medical information that may be disclosed inadvertently to others if sound transmission is not successfully addressed in the hospital. So making sure that there's minimal or negligible likelihood of those conversations being overheard is critical to those LEED for Healthcare projects. And our question: acoustic performance requires project teams to address which of the following? And the answers are 1, 2, and 4. Sound transmission, background noise, and mechanical equipment noise. Indoor environmental quality credit low-emitting materials. The intent is to reduce concentrations of chemical contaminants that can damage air quality, human health, productivity, and the environment. Now there's 2 options to this credit. First of all, the project can directly comply with at least 2 and potentially up to 7 categories. And we'll talk about those categories here in a minute. The next option, which we don't get into the calculation methodology behind it, but there is the potential to do a weighted average calculation based on the number of categories that are compliant and those that aren't, comparing the amount of compliant and non-compliant products that are applied within each of the categories. So it gets pretty complicated when looking at that calculation, but keep in mind there is a budget option. Now, looking at the strict compliance criteria, there are several criteria here that need to be addressed. So what we're looking at here are interior paints and coatings, adhesives and sealants, flooring, and then ceilings, walls, and insulation. Now, for each of these four, and we've got a few more to talk about here after these four, they either have one or more than one specific emissions and content requirements that they have to meet. So for interior paints and coatings, these need to meet both the general emissions criteria and the additional VOC content criteria. Now, for adhesives and sealants, these also need to meet both of these two sets of criteria. For flooring, it needs to just meet the general emissions requirement. So there are, of course, no wet applied products with your standard flooring systems, although there may be adhesives and the like included. And then for ceilings, walls, thermal and acoustic insulation, these likewise need to just meet those general emissions evaluation. Now, before we move on to talk about the remaining categories here, I wanted to say a couple of things here about these emissions criteria. So the general criteria here focus specifically on the emission of VOC content. And those are tested according to the CDPH Standard Method 1.1 2010, which is the California Department of Public Health Standard Method 1.1. And that looks specifically at VOC emissions. So the amount of volatile organic compounds that are actually emitted to the air. Now, the content requirements are completely different in that they do not consider how much is emitted to the air. They are concerned exclusively with the content of the liquid applied product. So we're talking the VOC content of paint. So how many grams per liter of this can of paint are volatile organic compounds. So we're looking on one hand at the emissions, and then on the other hand at the actual VOC content. So the emissions and content are two very different values that apply to these products. And the last three categories here are composite wood, and then the last two here are specific to only certain types of projects. So furniture is only considered if it's within the scope of the project. And if you recall from when we looked at the tables to get this credit started, there are tables with and without furniture. And essentially there's one more notch up or one more point required or category addressed required for projects that do include their furniture. And finally, for the LEED for Healthcare and LEED for School projects, recognizing that the occupants of these buildings have, well, in the case of healthcare, potentially compromised immune systems. And in the case of schools, they're likely children. And children have a lot less natural resilience to contaminants within their environment. Keeping in mind the strategies, first of all, establish a goal early during design and make sure that compliant products are specified. Now, you heard this a lot during the materials category, and you'll hear it throughout the remainder of the IEQ category here as well. Specification is really the key to making sure that the general contractor knows what to install and is contractually obligated to do so. In addition to making sure that it's in the spec, make sure that not only is it there in the general requirements, but they're also listed in each section where these products are detailed. So don't just bury those VOC criteria in the general section of the specification. Also included in paints. Also included wherever VOC, potentially VOC containing materials are included. So in the adhesive and sealant section, is probably flooring in your spec. Make sure that that's listed so that the contractor knows out of the gates what is and isn't acceptable. And we have a very specific definition what we mean by building interior. So keep in mind that for non-schools, non-healthcare projects, we're only looking at what's applied within the interior of the building. And in terms of how you define that specifically, we're talking within the waterproofing membrane. There are also certain types of products which are considered inherently non-emitting. Now, this is stone, ceramic, or the like that automatically comply if they have zero integral organic-based surface coatings, binders, or sealants. So if you have a brick that's certainly a ceramic product and it doesn't include any of these organic-based components, it's automatically going to comply. Now you can likewise have natural stone product, and if it's literally a natural stone that has no man-made additives to it, it's also going to comply here. The final thing I'll point out here is that assembly products are treated very specifically. So these assembly products that are 90% or more compliant, those can be counted as 100% compliant for LEED. Now, it doesn't sound quite that intuitive, but it keeps the calculation on the LEED user side very specific and relatively tidy. Now also, and I guess this is the trade-off here, is that products that are less than 50% compliant are considered zero. And we mentioned VOCs a moment ago, but here we define it specifically. A volatile organic compound reacts with sunlight and nitrogen oxide, or NOx, to form ground-level ozone. Now, ground-level ozone, which is quite problematic, damages lung tissue, reduces lung function, and makes lungs more sensitive to other irritants. It's also a major component of smog, so clearly something we want to avoid, and this is exactly what this credit addresses. And now our question. The spec writer for a LEED BD&C corn shell project is writing performance criteria for interior paints used in the shared common areas. Which of the following are important considerations when considering indoor environmental quality? Select 2. And the answers are VOC content and VOC emissions. Next, we look at EQ Credit Construction Indoor Air Quality Management Plan to promote the well-being of construction workers and building occupants by minimizing indoor air quality problems associated with construction and renovation. Now again, we look at a multi-requirement credit. Here we need to develop an IAQ plan for construction and those pre-occupancy phases of the building. Now this plan itself must conform to the minimum control measures from the SMACNA IAQ guidelines for occupied buildings under construction, 2nd edition from 2007. Now what's not addressed in those SMACNA guidelines is protection of absorptive materials. So we have a secondary criteria here that specifically addresses that. And next we have the minimum filtration values for our air handler system. So the return air grills need to include either a MERV 8 or Class F5, which is essentially the European equivalent to MERV 8 for those return air grills or the transfer duct inlet openings for any equipment that's operated during construction. In addition to that, final filters need to be installed immediately prior to occupancy, so you can't reuse these filters when the occupants move in. And then the final criteria here is that once the building's enclosed during construction, prohibiting use of tobacco within the building or within 25 feet, just like the prerequisite. But what the difference is here is that this represents prior to occupancy requirements around environmental tobacco smoke control. And our strategies. So first off, LEED for healthcare is different. So the requirements that we've laid out here do not apply to LEED for healthcare, as there are inherently unique characteristics of LEED for healthcare programs that are very different when it comes to managing the indoor air quality. Making sure that the IAQ management plan not only protects the HVAC system during construction, but also addresses pathways of potential contamination sources and interrupts those pathways. A key to successful implementation of this is to make sure that those subcontractors and installers are well informed about these strategies before they even start their projects, or their work rather, on site. If they are well informed, the likelihood is that they'll conform to these demands by the building owner and the general contractor and be a compatible team member when making sure this is successfully executed. There's also an important concept around sequencing the installation. So think about it this way. So if you were to install your furniture and then paint, so even if you can perhaps imagine that there's zero likelihood the paint is going to, say, drip on your new furniture, there's still the likelihood that unless that's a zero VOC paint, which I would recommend but isn't mandatory in LEED, could potentially emit those VOCs and they could be absorbed by that furniture. That's considered a VOC sink at that point, something that's going to absorb it. Those contaminants do not leave the space when they're absorbed by that furniture or any other VOC sink. So sequencing it so that there is not a VOC sink in place is one example of proper sequencing. Additionally, we have other credits that directly tie in here. So managing the indoor chemical and pollutant source control under the Enhanced Indoor Air Quality Strategies credit is a great tie-in here to this air quality management plan. And then we talked about the filtration requirements that are necessary when those HVAC or air handler systems are used during construction. So ideally, avoid using them altogether. Now, I completely understand that's not always possible, but where it's possible, put that into practice so that you don't need that extra expense and extra environmental impact associated with those filters that need to be installed and then replaced prior to the occupants moving in. And here we look at some real-life examples. So on the left-hand side, you see, well, on the top, I think most people would assume this is what not to do, and that's correct. We have some insulation that's sitting in a pool of standing water. Now, this is wrong on many levels, but the fundamental problem here is that this insulation, if it's later installed within the building, could pose a contamination risk when it comes to mold growth or any sort of deterioration that was accelerated based on increased moisture or even humidity within the wall chamber. Now, underneath that picture, we see how to do it right. So here we see the insulation remaining packaged until it's ready for installation. The other obvious takeaway from that picture is there's no standing water. On the right-hand side, we see two examples of proper duct coverings. Now, this represents the duct work as it's being installed in the project. So it would be typical for each individual piece of duct to be sequentially installed within the space to eventually complete the ductwork system. Here we visibly can confirm that there is coverings over these ducts as they're mid-installation. So see the duct on the top, we've got that cover across it. So say there's 3 days between that last piece being installed and them installing the next piece of ductwork. Now there's those same 3 days could represent an opportunity where maybe there's some cutting within the space or any sort of construction activity that would generate some particulate matter that can then settle in the ductwork itself and cause long-term contamination issues. Covering the ductwork prevents that from being a concern. And now our question. The intention to protect installed and on-site absorptive materials such as gypsum board is to prevent what? And the answer is moisture damage. Indoor Environmental Quality Credit, Indoor Air Quality Assessment. The intent is to establish better quality indoor air in the building after construction and during occupancy. Now there's two options here. First option addresses a flush out. This option is worth just one of the two potential points available for the credit. Now, the flush out dictates that 14,000 cubic feet of outdoor air be delivered per square foot prior to occupancy. Now, there is a caveat here that after a quarter of that's done, or 3,500 cubic feet per square foot, occupancy can be established. So that's what's called a phased flush out. But the standardized flush out requires the temperature to stay between 60 and 80 degrees Fahrenheit, and there's a Celsius equivalent as well, 1527, and that relative humidity not exceed 60%. Option 2 addresses air testing, and this is worth both potential points. There's a lot of contaminants that need to be tested for. We're looking for formaldehyde, particulates PM10, TVOC, or total volatile organic compounds, chemicals that are listed in the California Department of Public Health Standard Method version 1.1, referencing their specific criteria about those contaminants, and then carbon monoxide, not only in terms of 9 parts per million, but also no more than 2 parts per million above ambient levels. Additionally, projects that are located in the Environmental Protection Agency's definition of non-attainment areas, or whatever the local equivalent is for other countries around the world, must also test for ozone and particulates PM 2.5. Now, the strategies to keep in mind here, first of all, is that the project has 2 options, and they're very different options, and they represent different number of points. First off, a flush out is often used for projects that don't have very tight scheduling criteria. So when occupancy is not required immediately upon completion of construction, that leaves the opportunity for a flush out. Now, contrasted with that, we have the IAQ testing. Now, this can minimize the scheduling impacts. It's quite possible and feasible that the tester could come in and be in and out of even a large building within just a few days, whereas it may take a few weeks for the flush out to actually take place. The risk there is that there's the potential for non-compliance. So while it is absolutely feasible and quite encouraged by LEED that the project team only retest non-compliant areas if they need to come back in and based on a non-compliant result, it is never guaranteed that the IAQ testing is going to represent compliance by the project. And finally, all of this has to happen before the occupants move in. With the exception of the phase flush out, all the air quality testing and the flush out itself does need to happen prior to move in. And now our question. Which of the following would be factors that would encourage a project to undergo air quality testing instead of a flush out? And there's 2 correct answers here. And the correct answers are when construction's behind schedule and future tenants are ready to move in immediately, or the project is teetering between silver and gold. And let's talk about this for a minute. So when the project's behind schedule and they want to approach this credit and are essentially, as described in the question, on the fence between testing and the flush out. Now, when construction's behind schedule and the tenants are ready to get in that building, the flush out would create an additional delay. So for that reason, project teams may be pushed towards using air quality testing, as the question describes. The next reason, and this one's a little bit tricky and refers to the number of points that are available under each option within the credit. If it's teetering between silver and gold, it may be that 1 point, which is, keep in mind, there's 2 points for the testing and only 1 point for a flush out. So if it's kind of right on that cusp, that 1 point may make the difference. The project team may want to get there, and then they would more than likely select the air quality testing as a way to pick up an additional point. Okay, our next credit, EQ credit thermal comfort. The intent is to promote occupants' productivity, comfort, and well-being by providing quality thermal comfort. There's a lot of reference standards here, and we'll review many of these as we talk about the requirements. So first of all, there's 2 pieces to these criteria. First of all, there's design requirements, and there's also control requirements, and both of these need to be compliant to the credit criteria in order to qualify the project for a point. Now, looking at the design criteria, we have 2 different types of projects. So we have US projects and then projects that are not located within the United States. So for the US projects, they must meet option 1 here. They need to meet ASHRAE 55 2010, and that requires projects design their envelope and the remaining systems within the building to meet ASHRAE 55, which dictates thermal conditions for human occupancy. Now, there's special criteria for swimming pools, which is not well defined under ASHRAE 55. For option 2, we're talking about non-US projects, and for these types of projects, they certainly have the option to meet ASHRAE 55, but they can also meet those either ISO and or CEN standards so that they can demonstrate that the project is meeting the standard that's applicable based on its space type. And on the control side, individual thermal comfort controls need to be present for 50% or just half of individual occupant spaces and also need to be present for 100% of shared multi-occupant spaces. Now, before we talk strategies, let's review what counts as a control. Now, a control, as defined by this credit and really by ASHRAE 55, allows the occupant to adjust one or more of the following, which is air temperature, radiant temperature, airspeed, and humidity. Now, these are factors that, depending on the thermal systems within the building, may or may not be physically possible to adjust. Now, if you've got a forced air system, you're unlikely to have a lot of radiant temperature controls. And likewise, if you have a radiant heater within your space, there's probably not a humidity dial. But with all of this in mind, only one of these factors needs to be adjustable by the occupant in the space to be considered having control over the thermal comfort conditions of that space. So you don't need to address all four. A single one of these certainly complies the space. In terms of strategies, it really starts with design. So the mechanical engineer would typically sit down with the building systems and determine that the project is going to meet ASHRAE 55. And for non-US projects, of course, they have that alternative option here as well. That means that the system is going to satisfy the majority of users the majority of the time. The building envelope needs to meet these comfort conditions under expected environmental and use conditions. So you don't need to assume the worst possible case scenario where you've got twice as many occupants as typical and it's 110 degrees outside. Really we're looking at typical conditions. Now, the integrated approach is very important here. So there are a lot of factors. These four are specific to this credit, and using each of these and determining whether or not it's appropriate for the occupants in that space to have that adjustability is a great way to think about how you're going to provide that controllability to these occupants. And whenever we talk about thermal comfort, we always have to mention energy. Now, there's a lot of tie-in between energy use and how comfortable your building is. Now, if energy was never a factor, we could dial in temperature and probably keep most buildings, within a degree or two of a set point temperature. Now, of course, energy is not a non-issue. It remains an issue and it's very important to conserve. So balancing the needs of occupant comfort with the energy demand of the space is, again, one of those fundamental balancing acts of truly green buildings. Now let's take a look at a real-life example. So in this example, we have 12 individual workstations. Now 10 of these are provided individual thermal comfort controls. Now in this example, they're not described, but we'll take at face value here. There's 10 that meet the criteria. That's an 83% compliance rate, easily exceeding the 50% compliance rate according to the control criteria of this credit. Now the multi-occupant spaces, we have 5 here, and each of these are described. Now, reading through these descriptions, you'll quickly understand that there's direct thermal comfort controllability provided to each space within the space. So not only are we meeting 83% of individual workstations, we're at 100% of those multi-occupant spaces, easily meeting the control requirements of the credit. And now our question. An office employee can be included in the count of building occupants that has control over her own thermal comfort in which scenario? And the answer is 1 and 3. She has a private office with a thermostat on the wall, or she has an individual vent under her desk which she can open and close. All right, on to one of my favorite credits, the EQ credit for interior lighting. We're intended to promote occupants' productivity, comfort, and well-being by providing high-quality lighting. So now here we have 2 non-exclusive options. So option 1 can be elected in addition to or separate from option 2. But option 1 requires that individual lighting controls be provided for at least 90% of individual occupant spaces. Now, we're not talking on-off only, we're talking at least one additional level of controllability there. So it could be on and off and then kind of mid-range, it can have a dimmer switch. there can be a lot of options, but essentially giving occupants more control than simple on and off controllability. Now for multi-occupant spaces, we need at least 3 scenes, just like we did before, so on, off, and then somewhere in between. And there must be additional controls for projection or presentation walls. Now the final criteria here is that switches themselves have a direct line of sight to the light fixtures or luminaires that are being controlled by them. Now this is critically important. So many of us have found ourselves in a position where we're at a bank of light switches, and several of these switches do not seem to do anything, or certainly nothing visible from the perspective of the person at the bank of switches. What we're trying to avoid here is somebody fiddling with the switches, not knowing if they're on or off, and potentially leaving lights on when they shouldn't be, or vice versa. Now, option 2 gets pretty complicated, and we're not going to go way down the rabbit hole in terms of these complexities, but for option 2, the project needs to elect 4 strategies. Now there's just one here that I want to drill down into a little bit. Now that's number E. So we're talking about internal reflectance of the interior surfaces of the space. Now this is kind of a fundamental concept, so I'm going to take a moment here to talk about what I'm referring to. So the percentage here refers to the percentage of light that's essentially bounced off of that surface when a light's shined at it. So if you have an 80% reflective surface and you shine 100 units of light at this surface, 85 units are going to be reflected off and re-enter the space. So the higher reflectance you have, the better the light essentially bounces around within this space. So 85% is the benchmark here for ceilings, only 60% for walls, and what I think of as a relatively low number here, 25% for flooring. And now our strategies and terms. First of all, task lighting, which is essentially individual lighting control, needs to include that mid-level setting so that we are not focused specifically on on-off controllability, and there's at least somewhere in between that project users can navigate in terms of their lighting power. Now, for those multi-occupant spaces, there's a lot of different options. You can have bi-level switching, control panels, dimmers. You can have layered lighting, which is a term meaning that there's several different lighting quote-unquote layers within the space. So you've got your sconces separate from your overhead lighting that are separate from your desk level task lighting, and maybe those are separate from some ground level navigational lighting. Now all of these can be controlled separately, and because you can turn off one system versus another, that's considered a layered approach. So here's a quick example. Now we're going to look at the data from this project here in just a second, but we're looking at the floor plan now, and what we see here are the lighting controls, the different spaces, as well as how those controls interact with those space users. And now we define the number of controls. So this is the same space we talked about here just a couple minutes ago, and we have 12 of 12 individual workstations that have direct individual controls. Now that's 100%, which exceeds the 90% threshold required by the credit. We also are hitting every single multi-occupant space. So the dimmer in the first example, the dual level switching and occupancy sensor in the second, time of day and DDC, as well as the controllers mentioned in the third example, and the fourth example. So we're easily meeting the controllability criteria here, so the project's going to comply with option 2. And now our question. Which of the following scenarios would comply with a lighting control option of EQ credit interior lighting? Now the correct answers are 3 and 4. So we have a classroom with a dimmer switch and a conference room with bi-level switching. Now the daylighting sensor is a little bit tricky here. So let me clarify what we're talking about. The daylight sensor, which presumably would be connected with daylight responsive lighting fixtures, so that it's not just identifying the lighting level, but it's also then modulating those light fixtures to respond to the amount of ambient daylight, does not necessarily give any level of controllability to those space users. Now, It's great from an energy saving standpoint, provided of course it's daylight responsive lighting in addition to just the sensors, but it does not inherently give any controlling ability. So keep in mind, this credit is specific to allowing the user's adjustability. So whether or not it's dialed in 100% of the time does not necessarily give the users any control over that system. So really that's what we are getting at here. And our next credit, EQ credit daylight, is to connect building occupants with the outdoors, reinforce circadian rhythms, and reduce the use of electrical lighting by introducing daylight into the space. So we have several options here. And each of these options independently requires glare control for all regularly occupied spaces. Now, glare control can be delivered in a lot of different ways. It can be blackout glazing, say at the very high-tech end, or it can simply be some architectural shading devices that were installed maybe outdoors adjacent to the space. But within these three options, they kick off with the simulation, spatial daylight autonomy, and annual sunlight exposure option. Now this one gets a little bit tricky and goes well beyond the calculation methodologies that LEED has been accustomed to under version 3. So we're looking here at the spatial daylight autonomy, which is different than the illuminance that we'll talk about here in option 2. Now if 55% autonomy is achieved on an average basis, the project's going to achieve 2 points, and if 75% is hit, you'll get all 3 points. The computer model, because really this does require computer modeling, must also show that sunlight exposure of no more than 10% is achieved for those daylit areas. So you're not getting overwhelming direct sunlight penetration, which causes glare problems, but also heat gain problems and the like. So that's minimized while still maintaining the very high levels of daylight autonomy. Now the next approach really looks at the light levels themselves. So not the percentage of daylight, but actually the amount of light. And this requires a daylight model, similar to the first, but here we're looking at illuminance rather than spatial autonomy. So here we're targeting between 300 and 3,000 lux. And if you hit 75% of the floor area, you'll get 1 point, or 90% for both points. And then finally, we have the measurement option. And I'm very pleased to see how they've ranked this one in terms of points and offered the full amount of points under this option. So this represents physical daylight measurements of the real space after it's completed. So you'll literally go in with a illumination meter and you'll measure the light levels at the workstation level. So typically 3 feet above the floor, you'll measure that at 10-foot intervals or so throughout the project and confirm that 75% for 2 points or 90% for all 3 points of the regularly occupied floor area is between 300 and 3,000 lux. And now our strategy. So first off, this one sounds a little bit remedial, I suppose. So design the building to maximize daylighting. Now, that's actually really important. So when the project team sets out to design themselves a building, there's a lot of different things they're thinking about. I can only begin to imagine how many different concerns that are on the architect's mind when they set out to make a great building. But one thing that should be front and center is how to maximize this daylighting. And if they're thinking about that early on, odds are that they're going to have better opportunities down the road. Now, some strategies to think about are the orientation. First and foremost is the building orientation. So whether it's east-west, north-south, what have you, making sure that the geometry of the building itself, and primarily the orientation, is going to facilitate effective daylighting strategies. Some other strategies to mention here are shallow floor plates, increased perimeter, but also these permanent shading devices, as well as high-performance glazing, high ceiling reflectance. And we talked about reflectance a few minutes ago, and here's where it again starts to play into effective daylighting. Absolutely automatic photocell-based controls. Now, daylighting inherently by itself, energy saving aside, can be a good thing. There's some studies out there that show that increased daylight is great for a number of reasons, including, and somewhat contentiously, increased retail sales. So daylight itself as a relatively good thing is awesome. But we can also leverage daylight to save energy, but only if we have automatic photocell-based controls, so that as that daylighting comes in, the lights are tuned down so that the amount of energy provided to your lighting system is reduced based on the amount of daylight you're getting to the space. Now, we talked about these daylighting factors and luminance calculations, and they do get pretty complicated. So making sure you're engaging a competent modeler, computer simulation modeler, is really important here. And then finally, I'll mention what many of us, and myself included, were more familiar with prior to this edition of LEED in terms of units of measure, and that's foot candles. So foot candles is directly equivalent to lux, and we have the conversion factor shown here. And now our question. Providing occupants with access to daylight could what? Go ahead and select 3. And the answers are 1, 3, and 4. So increase energy demand of the building, decrease energy demand of the building. We'll talk about that here in a second, as well as increase productivity and potentially happiness. Some people might claim that this is a tricky question, and I wouldn't completely disagree with that, but it is reflective of what you could potentially see on your exam. So let's talk about these first 2 potentially correct answers. So increase energy demand, decrease energy demand. So keep in mind, daylighting itself is not inherently an energy saving or an energy spending strategy. It could, by increasing the daylight in a building, you could increase energy demand or decrease energy demand. And a lot of that's going to depend, first of all, on the climate. So if you're in a very hot climate with a lot of direct sunlight exposure, and say, for example, you're putting your glazing on a side of the building that would see a lot of direct solar penetration, your cooling energy that's required to then offset that additional solar heat gain could be more than the amount of energy you save on the lighting side. Now, the opposite's also true. It may be that the cooling energy demand that's increased potentially from having additional daylighting systems within the building may be small compared to the amount of energy saved on the lighting side. So we don't know at face value whether daylighting is going to increase or decrease energy use. So it's quite accurate to say that access to daylight could increase energy use or it could decrease energy use. Now, clearly it won't do both, but without knowing more about this system, we have no idea whether it's likely to increase or decrease that usage. And our final credit of the category is EQ credit quality views, where the intent is to give building occupants a connection to the natural outdoor environment by providing quality views. The requirements are that 75% of regularly occupied floor area achieve a direct line of sight to the outdoors. Now, that same 75% rather, must meet at least 2 of the following criteria to have what are considered eligible views. It must be multiple lines of sight, at least 90 degrees apart. So you're looking at a window to your right and you're looking at a window to your left. They're at least 90 degrees apart, and all of a sudden that's a compliant view. Or the view can include at least 2 of either flora, fauna, or sky, movement, or objects that are at least 7.5 meters away, or 25 feet. The other 2 criteria are either unobstructed views, relatively close to the window itself, or within 3 times the head height, or views that achieve a factor of 3 or more, according to the reference standard. Now, there's a lot of strategies here as well. So keep in mind, we're talking about vision glazing. So you can't just have a translucent window that you can't actually see any objects through and say, hey, this counts as a view. Because vision glazing provides a clear image of the exterior. It's also unobstructed by fritz, fibers, pattern glazing, or even added tints that distort color balance. Now, thinking about how those view angles are tallied, first of all, we do not include any movable furniture or partitions, but we do factor in any permanent interior obstruction. So knowing what to factor in and what not to factor in is going to be really central to successfully documenting this credit for LEED purposes. Atria. Now, these can count up to 30% of the required area, can have views into an atrium space. So maybe those very large buildings that have an atrium to help mitigate that, the fact that their perimeter is relatively small compared to their total floor area. Big buildings are inherently burdened with that problem. They can use atrium to address that. Now, quite simply, design the space to maximize daylighting, but also views. So thinking about daylighting and views in tandem is going to give projects a lot of synergy in terms of how they're addressing these concerns. Now, the most important consideration when looking at daylighting, but also views, are those interior partitions. So making sure that those have been designed in a way to minimize the restriction of access to views to the exterior. And finally, direct line of sight to perimeter vision glazing is really what we're talking about here. That's the name of this game. So if the building user has that direct line of sight and meets 2 of those 4 criteria we talked about a minute ago, they're going to meet the requirements. And finally, our question. Which of the following areas would count against the project when assessing compliance with views for LEED? And the correct answer is number 4, that janitor's office that does not have access to views. That would count against the project, or essentially count as eligible floor area, but not as floor area with the access to views when tallying compliance.